compared to bulk, there is a lot of confinement effects. So that's what we mean by capillary. We build up these capillary models using one approach, which is the Landau-Degen type of approach based on the Q-tensor order parameter. So it's one model. It's a blue suit fit all occasions. You can go to a wedding, to funeral. One model fit everything. Okay? So with this, I cover like 16 topics on Monday based on the physics of in the Landau-Degen type of model. What remains is talk about shape equations. So what kind of equations do you need to describe the shape of nematic systems, which is different than isotropic system? So because you have a shape which is described by a curvature tensor, right? And then you have a Q tensor interacting with the shape. So you have two things talking to each other, shape and structure. So shape interacts or responds to structure. If you have isotropic liquid, you just have a shape, and here you just have a scalar, which is a pressure. Of course, here we also have scalar information. So that's the nature of the problem, the interaction between shape and structure. And that's what I will describe, how to derive the shape equations, and then move here and do a little bit of thermodynamics and try to show how thermodynamics tells you that you can change the shape of things, changing the temperature and changing, for example, the interfacial tension by adding surfactant. So we'll show that if you have a nematic drop of this type, adding surfactant to the system can change this drop into a fiber. So that's something, an effect not seen with isotropic fluids. You can manipulate the shape of things with a chemical potential. And in addition, we'll also talk a little bit about more novel, newer systems where you have, for example, multiple order parameters. You can have a conserved order parameter, which is concentration, mass is conserved, and that's coupled to non-conserved order parameters like here, the Q tensor, but we add a little bit nanoparticles. Is going to be another non-conserved order parameter, and these nanoparticles can crystallize. So you want to have a system that has crystalline order coexisting with orientational nematic order. And depending on how do I go about the speed, I talk about some applications. We have lunch, and then we'll see how much I can say about films. The interesting points about these nematic films are, for example, if you want a coat, a fiber, what is the relation between the speed at which you drag a fiber on this nematic fluid? What is the stability of your films? If you have a nematic foam, you want to support the ligaments between the nodes. So for that, you need to understand film stability in nematic systems. Talk a little bit about membranes. For example, this is all bio type of motivated systems. For example, the plant cell wall can be approximated as a two-dimensional anisotropic soft matter system. The cellulose playing the role of rods, and the pectin and the matrix playing the role of the elastic membrane. So, and if I have time, I say something about fibers. With Jimmy talked about railing stabilities, and here we like to show a new type of fiber instability, which is a chiral instability, which, by the way, is in the book of Levitch. The book of Levitch has, those of you who maybe have access, is a older but excellent book on physicochemical hydrodynamics. He shows that a fiber can also undergo chiral deformations as opposed to breaking into drops, the peristaltic mode. Okay, so this is what we're discussing, liquid crystals. So we have order parameters. So here we come down, we inject thermal energy, we melt typically position, and we retain here some positional order in columnar or one-dimensional order in smectics. You inject more thermal energy, and you have a nematic fluid that has only a Q-tensor orientational order. You can add a little bit of chiral compounds and give it chirality, for example. And interestingly enough, you have a one-to-one correspondence between the order parameters in your system and the mechanical behavior of the system. So here we have an isotropic elasticity corresponding to positional orientational order. Here in this, if you consider nematics, we have an isotropic viscoelasticity. And the key words for liquid crystals are anisotropy, right? And in addition, a key part of the physics is the presence of topological defects. And that was the 2-lecture series of Kamian last week. So he spoke about defects in crystals and liquid crystals. So I build up on what he said. I also will build up on the 2 courses by Professor Stewart on Leslie Erickson nematodynamics. So these 2 things appear right here in the anisotropic viscoelasticity. So let me just put this in context. So for the last kind of 50 years, starting, well, it goes back, but the renewal effort by Osen was mentioned here earlier, yesterday. Osen and Frank took up this work of renewing liquid crystal elasticity some 60 years ago. From 60 years, a lot of physicists, mathematicians, engineers all contribute to evolving, converging into this theory of bulk nematodynamics, which can be in the simplest form expressed in these 2 terms. One is this is the dissipation, the rate of entropy production. It has a viscous part. T is the symmetric stress tensor. A is the rate of deformation tensor. And has internal degrees of freedom, so we have internal dissipation. This is what I called before the molecular field, is that field that acts on the Q tensor to distort this ellipsoid. And this derivative is called the co-rotational derivative, dq dt. And from that, you have to subtract rotational motion of your underlying media. So it's a special type of derivative similar to what Jimmy discussed yesterday about the upper convective Maxwell derivative. This, you have to subtract the rotation. So you only take into account the rotation of the Q tensor with respect to the rotation of the fluid. Otherwise, it's non-objective. So this kind of form the basis. Here you have a lot of the elasticity of Frank, of Sen, and other people. And from here, a lot of people contributed to developing this kind of irreversible thermodynamics to obtain the symmetric viscous stress tensor and the velocity of the Q tensor in terms of the rate of deformation tensor, the rate of strain tensor, sorry, in the underlying fluid, and this molecular field. So this system is viscoelastic. And here we have a matrix of viscoelastic coefficients, which were part of a lot of practical investigation by rheologists, by all kinds of people. So there were a lot of statistical mechanics that went into constructing this matrix and a lot of experiments. So all these years, we have a very good handle on bulk nematodynamics. So based on irreversible thermodynamic treatments. Then we go into modeling. A lot of people have worked very hard in trying to understand this coupling, which is the essence of liquid crystal flow problems, is you couple the flow velocity with the Q tensor velocity. So it's a coupled system. Here you have Navier-Stokes. Here you have the Q tensor dynamics. They are coupled into this cycle. When you ignite this part here of your matrix, you consider flow-induced orientation. That's what people in polymer processing does, or nature uses to orient. This is, for example, flow by refringence. If you have a random assemble of rods, you impose a flow, you create flow, streaming flow by refringence. So this is the effect of that you obtained by igniting this part of the matrix. When you come here, then you say, what is the effect of Q velocity on the flow velocity? That's what we call hydrodynamic interaction. In liquid crystals, it's known as backflow. But what does orientation change do to the flow kinematics? So like here, you have two branch point effects here. They come together, and they create vorticity. So the approach of this point effect with this point effect together creates a vortex flow. So to understand this, you have to understand the coupling between Q velocity and flow velocity. The effects, as you can see, form the basis of nematodynamics. So typically, a lot of people spend a lot of effort trying to understand nucleation, annihilation of topological defects in the flow. So that was, this effort still continues. And the problem with these topological defects in complex flows, you don't know where it appears, where annihilation and nucleation is. So this is an example of defect nucleation observed experimentally when you have a shear flow close to a surface and the system in this tumbling mode we heard yesterday. So if you have tumbling orbits close to a flat surface, you're going to nucleate a defect. So defect nucleation, anytime you have a defect, is because you have frustration. Is the system displayed like bad temper? It is frustrated. So you have orientational frustration. So the way to relieve frustration, that is orientation gradients, is to nucleate topological defects. And here you have parametric phase space. A lot of experimentalists have worked very hard. At the simplest possible level, you have a dimensionless concentration or dimensionless temperature, whether you have a lyotropic system or a thermotropic system. You have a ratio of time scales. This is orientation time scale, and this is a flow time scale. This number is called the Ericsson number. And you have a ratio of length scales. This is your system size length scale, and this is your internal length scale, which is the length scale of this point here, of a topological defect core size in the nanoscale, and that's square. That's why, and the ratio of these the time scales to square of length scales give you the famous Deborah number. So the key point in the rheology of the systems, whether your Deborah number is large enough, so you have molecular elasticity, or whether your Ericsson number is large enough, you have orientationally macroscopic elasticity. The other key point, so this is beta parameter that refers to the geometric content in your system. That is whether you have rods, whether you have disks, whether you have plates, whether you have something else. So here, this geometric parameter is just one single scalar approximation. There's a lot of work being done on putting better geometric information on these equations, still going on. The whole point here, when you augment all this treatment with computation, we want to do computation, we have to take into account this parameter, which is for real numbers, H over L square is 1,000,000. So you do PDEs with a parameter that is of value is very large, 100,000, 1,000,000. So this is the size of your shear cell or rheometer to the site of a topological defect. So if you do microfluidics, nanofluidics, you're okay. Yes, Jimmy.
Wouldn't I consider the elastic coherence length instead of the core size in constructing that ratio?
So this typically gives you a good definition of an internal length scale. This L is L is the square root of a characteristic Frank constant divided by the first term in your Landau expansion. Yeah. Yeah. So this is now we need the computation. So this work we did with Tomohiro. So this what the first thing we try to capture is quenching into the nematic phase. These are 3D periodic box creating the so-called Kibble mechanism that tells you that when you quench, you have a massive disclination state, the coarcents, because these lines, as you can see here, are elastic strings that have a line tension and a bending tension. So we were able to reproduce this and subject it to a shear flow, and you can see like loops straightening and shrinking like there. You can see more complicated phenomena. For example, this loop and this loop interacting and disappearing. So you have right there, for example, you have all these topological defects. In addition to loop shrinking, you have some basic topological phenomena that your simulation has to capture here. Is you can have a disclination line that shrinks, for example. You can have two disclinations of different sign interacting through elastic forces and annihilating. You can have these T1 and T2 topological processes where lines converge and depend. So all this had to be part of your soup. So these were well described some years ago with our Q-tensor equation that is very similar to everybody else. The only thing is we ran this at that time with the best available supercomputers we had at the time. Yes?
How exactly are you identifying the position of the disclination?
Okay, so these were extracting all what is S, not equilibrium, and S very close to the environment where you have a topological defect.
The magnitude of the...
Yeah.
Are they one-half disclinations?
We have 1/2, minus 1/2, we have +1, -1.
In this spaghetti soup.
In this particular one, we have 1/2, minus 1/2. So the question here is how we visualize this. So this is the biaxial order parameter. So it has two scalars, S and P. So all the states in the system are contained in this triangle that goes, S goes from 1 to -1/2, and P goes from -1.5 to 1.5.
And M and L are the physical axes.
Yeah. And then you have these biaxial lines. And these are the important lines. This is the line P equal to 3s. So every state in the nematic inside this triangle is biaxial. And then you have three important lines: the horizontal line and these two oblique lines. In these two oblique lines and on this horizontal line, you have uniaxial states. Therefore, these topological defects we look in, they live on this uniaxial line. On the P equal to 3s, it's a uniaxial line. So a topological defect is a connection, like I described the other day, a sink-saddle connection. This is a sink, it's a stable root of your free energy. This is an unstable saddle in your free energy. And a topological defect is a little connection.
I always thought that most pneumatic systems in their ground state, there's no defects, you just have uniform boundary conditions, that they most often you find uniaxial pneumatics.
Yeah, so if you run this forever without flow, it will coarsen. The two
wind up on one of those three lines.
Well, no, in this line. This line, that's the key root. And the reason why is that's the lowest energy state available close by is going to go there. And the two ways, the key ways that is observed, pneumatic fluids eject disclinations is by this coarsening process I described before, annihilation, loop shrinkage, etc. Or if you have like a box like this, through the boundary, a defect can exit, can get rid of, leave the room. Right? So these are the two different ways. The key point is, for example, if you deal with liquid crystal polymers, it's very hard to have a monodomain. So if you look in a polypeptides, DNA, Kevlar, any kind of man-made or biological liquid crystal polymer, for various reasons, including high viscosity, the disclinated state, polydomain state, is what is observed. I know after all these years working in this field, only two groups that were able to do liquid crystal polymer monodomains. The Guy Berry, for example, and Brandeis. Very few people are able to do a liquid crystal monodomain. So the key point was capture this Kibble mechanism, this formation, annihilation of topological defects.
My point is just that in that picture, almost everything.
We extracted the nematic phase and left only this root in space. The rest, everywhere else,
it's uniaxial.
you have a nice uniaxial system. Yeah.
So you're identifying the places where there's appreciable biaxiality.
Exactly. Well, no, it's these points in this periphery. These points are what we call uniaxial because P is equal to 3s.
I mean, almost the entire volume is uniaxial.
Yeah, but this is a different type of biaxiality in which, if you think in terms of an ellipsoid, you go from prolate to oblate.
Oh, so you're identifying the places where it's most oblate, which is the opposite of what the system wants.
Yeah.
Okay, thank you.
And the second step, that still ongoing process, so that was simulations in the late 90s, was to start doing coupled flow problems. So here we coupled the fluid mechanics, fully coupled, with the Q tensor dynamics. So this also we worked for 10 years with 50 people, the National Science Foundation of Center of Advanced Fibers and Films. So there were a lot of people involved, and one of the tasks was to come up with a solver for these nematodynamic equations that are fully coupled to the Navier-Stokes equations, and we achieved 2D transient solutions, solved for pressure, for the three velocities, and for the Q tensor. And so this shows a little bit where we are. So the top figure is just the velocity in the z direction. So this red is plus, blue is minus. That gives you an indication that flows go out and into the page. So you have secondary transverse flows that have to obey mass balance. So that's why some flow is coming out, some flow is going in. And at the same time, here we show the formation and stability of topological defects. This is shear. This is two-dimensional system, a flat fixed plate. The top plate is moving with a prescribed velocity. We have a velocity field. We don't know what it is. We have to capture. You see here the coarsening very slow. Why is very slow? This coarsening because it's impeded by the flow. So here you have two topological defects that are attracted plus and minus 1/2 under flow. And this flow slows down the coarsening dynamics in this particular case. And we are able now to predict, for example, stable structures like this array of topological defects. Yeah, you have plus, minus, right, in two-dimensional flow in a fully coupled system.
Why did it Your array only has 4 elements. Why
right here?
Yeah, why doesn't the chain continue?
Now it's stabilized. I had more, they coarsen. This is the size of the cell we were able to capture. The one point is the distance between topological defects in all liquid crystals. The external length scale controls the orientation. So this distance is of the order of magnitude as the gap thickness.
Right. No, but I'm just wondering why you've only got an array on one side of your cell.
I had some left over here, this noisy system. They have plus and minus. This is a good point. So, for example, it's very hard to get topological defects close to each other of different signs that are fully stable. Of course, this is a non-equilibrium system. So, for example, I will show maybe later what's happened in the spider duct. The spider silk is a liquid crystal, and you have a duct flow. And you can see there a very nice stable topological defects that then evanesce and disappear. So I had some topological defects there. They nucleate at a distance that is scales with the gap thickness. If that distance between defects is below a threshold, they will come and disappear. They can easily talk to each other. They are talking to each other. It's plus, minus, plus, minus.
Keep running the simulation, those 4 are also going to disappear?
As far as we were doing this for a long time in characteristic time scales we're interested, which is spinning fibers, is in the microsecond time scale. This will persist.
What is the feature of the flow that stabilizes them? What particular feature of the flow?
The particular feature of the flow is this. To have topological defects interacting and annihilating, you have to have rotation. The director has to rotate. You have a plus and a minus. And this rotation now is being controlled by flow torques. So the flow torque dominates over the elastic torque. That's the feature. Yeah, exactly.
Okay.
Yeah. So given this, I just chew up 20-something minutes, but I'm going to continue the lecture on interfaces. So that's the background. That's our background, the context. So now we try to move, me and many other people, into this new area of nematocapillarity. So we have structure, we have shape, we have stability issues. So the type of problems that are of interest to a lot of people right now in this community involve films, foams, and coatings. So they are all reduced dimensions. You have a smaller cross-sectional dimension as in a foam. You have coating flows. You reduce, you have a small dimension in the system. So you have confinement and you have curvature. Fiber spinning continues to be a lot of importance. It's an industrial process. Carbon fibers, for example, spin from carbonaceous mesophase pitches. Here you have biological fiber spinning, like spider silk, which the dope is a liquid crystal. So in these problems, you have structure, shape, confinement. And this area is very active now, active anisotropic membranes. So here, the difference is you have a membrane, you have membrane elasticity, you have bending and torsion resistance. So that's a membrane. You have a resistance to bending and torsion. So that's described not only by a Q tensor, like in these systems here, you can do well with a Q tensor. Now you have a membrane. The membrane has resistance to bending and torsion. So you have to augment your description with a curvature tensor, which is just minus the surface gradient of the unit normal. So that is the way to handle these important new problems of anisotropic membranes. So you have an elastic membrane that has anisotropy, it has orientation order, has a Q tensor attached to it. In addition, like motivated by biological membranes, liquid crystals are known for multifunctionality. One of those functionalities is called flexoelectricity. So that means the system can develop polarization upon bending. So in a biological membrane, that's manifested by the production of a potential. So this is a lipid bilayer. We have many of those in our body, especially in the inner ear. In the inner ear, you have something called outer hair cells that allows you to hear. The outer hair cells acts like a small microphone inside. It doesn't send signals to the nervous system. No, you have like 30,000 outer hair cells. Once you kill them, forget it. There is no remedy. There is no implantation for outer hair cells. And these outer hair cells, what do? They use flexoelectricity polarization. So a sound wave comes, it creates a periodic polarization through the bending of the membrane. And this bending, right, is encapsulated in viscoelastic media inside the cell and outside the cell. So you are in contact, you have a flexoelectric membrane which is moving. This is a nanoscale bending, is bending and pushing viscoelastic fluids in the surrounding media. So that's another example. And drops, we heard several talks on liquid crystal drops. So the material engineering problem here is how to create and use these polymer dispersed liquid crystals. Sometimes this can be an emulsion, or this can be a cross-link polymer, and use it for electro-optics. So in all these problems, the key words are how to be able to model and describe structure, shape, and stability. So we used, as I introduced before, the Q tensor. For interface and membranes, we use the B tensor, the curvature tensor. This is a very useful decomposition. H is the average curvature, and D is the deviatoric curvature. If you have a sphere, D is 0. So anytime you have non-spherical shapes in a liquid crystal, we always, most of the time, might have non-spherical shapes. So this decomposition is very useful. I and Q are two of the four bases for two-dimensional tensors. So any two-dimensional tensor can be decomposed into these four modes. And so you have 1, 1, 0, 0. So you have 1 minus 1, 0, 0. You have 0, 0, 1, 1. These are the Pauli matrices. So these two bases allows you to describe any symmetric tensor. So that's why we and other people are use this routinely, the curvature tensor. And for filaments, contact lines, problems, you use the Frenet-Serre formulas. So for this kind of problems where you have membranes, you have to couple Q and B. And this coupling of Q and B describes anisotropic membranes. For contact lines, you can couple Q and T, for example. So this is what I did last time. That was what I did on Monday. I went through the order parameters. I described all the physics insights you get by looking at this ordering triangle. I went on to present the free energies we use. The key point is for liquid crystals, you have an anchoring energy at the surface and at the contact line. And with these simple energies, using simple calculus of variations, you can easily derive the stress tensors. So we derive the stress tensors in 3D, in 2D, and in 1D, right? All systematically. And then we showed that there is an intrinsic connection between the divergence of stress tensors and the molecular fields, which were the variational derivatives with respect to the Q tensor. So the two are talking to each other. So in the static limit of nematostatic, you have only one shape equation for the shape, and you have two shape equations for a line, bending and twisting. Now I proceed to shape equations that were the title of talk number 1. So this is motivated. So we do have a phase diagram that tells you what is the shape of tactoids and drops, etc. So this phase diagram is derived and explain a lot of the physics using this type of surface free energy. It has an isotropic component and an anchoring component. So this surface energy depends on the inner product of the Q tensor and the unit normal, K. And this is the simplest one constant approximation of Frank. So with these three parameters, the isotropic tension, the anchoring, and the Frank elasticity, you can construct this phase diagram that captures a lot of the physics observed and predicted by other means of pneumatic drops. So basically in this diagram, we plot the anchoring as a function of interfacial tension, the isotropic component here, and on the horizontal, the ratio of Frank elasticity divided by the isotropic component of the surface tension, and R is the characteristic size of the drop. So basically, when you have stronger anchoring, when W grows and grows, you go from an homogeneous orientation field, in this case vertical. This all examples is when the drop wants to be, the orientation wants to be tangential. So when you go up, you're going to see that whether you have large drops or small drops, you're going to have a transition here from homogeneous orientation to, in this case, bending orientation with bending, and with the formation of some topological defect charge in the top and bottom south and north pole. And when you when you decrease the size of the drops, you go from mainly spherical drops to spindle-like drops. So these spindle-like drops, they can be without a geometric shock, or you can have a geometric shock on a macroscopic sense. And when you go up, here you have things called bogiums with the topological defects and the spindle-like shape. So what I'm doing here is based on this Landau-Degen formalism I spent Monday talking about, can we derive some basic equations that generalize this diagram to more energies and other cases? So an equation. So what kind of equation we can use besides, scaling or numerical methods? That is called the shape equation. So to derive the shape equation, you can just go ahead and try to reproduce what other people do for isotropic liquids, and it becomes like a zoo. So I said to my student, John, there might be a better way to derive shape equations for liquid crystals. So the best way to proceed further was to use this Kahn-Hoffman capillary vector. So as the word says, it's a vector. So it has two components. It tells you that to do capillary physics with liquid crystals, because the system is anisotropic, you want to use vectorial quantities, at least. So we use the simplest vector you construct from the interfacial tension, which has a normal component. This, in what follows, due to merging of different papers and different nomenclatures, I use gamma or F sub S. So this is the Kahn-Hoffman capillary vector associated with a liquid crystal. For a crystal, and there is no explicit orientation in the formula, so it's always a scalar, gamma prime, gamma double prime. Here you can see, because this free energy F is a function of Q and K, we have a nice expression with a normal and a tangential component. Physically, what does it mean? That you have a normal and a tangential component of for capillarity. It means you can change the energy of the system by changing the size. So that's the meaning of this vertical arrow, which is acting in the opposite direction as the area vector. So that tells you the way to reduce energy is to push it in and decrease the size. So that's this effect here. This effect is you want to reduce energy by reducing the size. And this effect here tells you that you can escape unfavorable orientation by tilting the surface. So here you have to think in terms soft and hard modes. You have a shape and you have structure. You can have a hard surface and a soft orientation field, or you can have a soft surface and a hard orientation field. So you have 2 degrees of freedom to play, shape and structure. So what this tells you, that from this point of view, from the capillary point of view, the interfacial tension point of view, the shape point of view, that you can escape unfavorable orientation by changing the shape. That's what it means physically. And the other key point from this expression is that now your surface interface is equipped with a main frame. An isotropic system has no main frame. So you have a patch of a simple liquid, for example, and the only thing you have is a unit normal. That's it. That's the only frame vectorial information associated with a surface patch. Now, with a liquid crystal, you have a main frame. So you have a T tangential vector, which is the projection of the director on the surface. That's the tangential vector, T, indicated here and there. That's the projection. It's a unit vector that is the projection of the director orientation on the surface. And B is the torque axis. B is the cross product of K and T0. So that means that the way the surface escapes a bad situation is by tilting along an axis which is defined by B0, which is the cross product of k and t0. So the only time you don't have a main frame is when the director is in the perpendicular direction. Otherwise, you're going to have a main frame. So when you have a main frame, this is what happens. You have torques acting on the Q tensor. These torques, they operate on B0, and these torques can be clockwise or anti-clockwise, depending on whether the anchoring lowers its energy in the planar mode or the homeotropic mode. Of course, you can expand it. Yeah, you can put more bells and whistles. You can put azimuthal components of the tension. You can do tilted orientation, but this is the basic of the system. That the key message is you have a main frame and that we have a torque. And this torque will never disappear unless the director is in its lowest energy state. So now when you have this, what time is it? We have to go to lunch or what? Eh? Okay, let me just finish this. Let me just finish this. I do my last point here, which is very important. So once you have this new capillary vector for liquid crystals, you can compute bending stresses. Bending stresses is what decides the shape. So you have a main frame here, B0, T0. There lives a cylinder. This is called the bending stress cylinder. And on this cylinder, if you draw on the surface of the cylinder a vertical line, it tells you how strong is the torque to tilt out of the bad situation. So here the torques are 0, and they increase more and more as you deviate from the torque axis, which is B0. So we'll use this in the shape equation. The fact that the bending stress, which is a 1-3, 2-3 component, arises because we have anchoring, right? And that's what decides the shape of things in the kind of metallurgy. It's called the Herring's stress, which he put it in for metallic systems. And the second important point is when you do contact line problems, you have contact angles, right? You want to understand what is new with a liquid crystal when you have contact angles. Is the simplest possible way, more revealing way, is to use this Kahn-Hoffman capillary vector, right, to compute the force on a tangent, on a unit tangent T. So this is T, this is the unit normal, and you want to know how do I compute now the force on this T. And to compute the force on a unit tangent, you just take the cross product of the capillary vector with T. Now, here you have two components. One was the normal component, the other is tangential component. Here I put it in red and purple. So this is the area size dilation component, and this is the tilting component. So when you take this cross product, you get two terms. One for the red, one for the purple. This is what you get from the area size dilation component. This is a contact angle, substrate, pneumatic liquid crystals, vapor phase. This is the vapor liquid crystal interface. This is your Young-Neumann force, which is always parallel to the surface, as indicated here. It's on the surface because T cross product with K, it has to lie on the surface. So this vector is a tangential vector. And when you do the same calculation with the normal component, the tilting component, you take the cross product of T with the component of this tangential vector, and you're going to get a normal vector to the surface. So this purple component tells you that at the apparent contact angle, you have an anchoring surface, a tilting surface, a tilting area effect that is perpendicular to the surface, not tangential. So now when you do this problem, the contact angle problem for a liquid crystal, you don't have a Neumann triangle, you have a liquid crystal pentagon. It's a pentagon. You went from a triangle to a pentagon. The triangle is the three forces you know from Young Neumann. For a liquid crystal, you have perpendicular forces from anchoring. So you have a pentagon, and it comes directly from the definition. So we go for lunch. So then we continue with this.
So is there some immediate question? Well, otherwise,
Otherwise, yeah, we go for lunch.
we will reconvene at 2 o'clock.